It's a great pleasure to introduce Manos Chatzopoulos. I came to meet Manos quite a few years back when he was an undergraduate student here in Crete, and he decided to do his undergraduate thesis with me. It was a pleasure working with him. He's a talent. He was a very talented student back then, very passionate. I'm not exactly sure if this is the same, if he has the same feelings. I mean, I'll give you a hint. We were working on AGN variability on very long time scales, I mean years. And what does he do when he goes to work for his PhD thesis? He goes from AGN supermassive black holes to tiny little stars, and he goes from long time scales of tens of years to seconds, right? So you can understand how much he loved it, right? Anyway, so when he left Crete, Manos went to Austin, where he did his PhD, and then he moved to Chicago for his PhD, and now he's an associate professor at the Louisiana State University. I am very, very glad to see Manos progressing from a young, talented student to an experienced and respected scientist right now. So it's a pleasure, Manos, and without any more delay, the floor is yours.
Well, thank you very much, Yosef, and everybody at the Hellenic Astronomical Society. It's really an honor, and I do want to give a special thank you to people from the University of Crete who gave me a really strong foundation over the years as an undergraduate student to help me be where I am today. And I hope that by the end of this talk, I will convince you, and you will also have Betelgeuse as your favorite star in the Milky Way galaxy, as it is definitely my favorite star in the Milky Way galaxy. I would say right after the sun. I guess the sun is still very important, keeps us alive. But a second favorite star in the Milky Way galaxy is Betelgeuse. And there is a lot of indication that Betelgeuse has a couple of really interesting properties that, according to our latest work, point to the idea that perhaps it suffered in the distant past a merger with a smaller companion. And by the end of the talk, I hope that I will convince you that that case seems to be supported by data and observations. So when I use the word Beetlejuice, I do not refer to the old movie Beetlejuice that, Halloween is already well behind us, although 2020 keeps being as scary as it was back in November. And it's actually even spelled a different way. As a matter of fact, when I use the term Betelgeuse, I'm referring to this very red, beautiful, bright star in the upper left arm of the constellation of Orion. And both me and you were fortunate, I guess you can call it fortunate, to live in the northern hemisphere, where we can easily enjoy the awe and the beauty of this constellation. It's one of the most famous constellations in the night sky. Every time I ask my undergraduate students, name a couple of constellations that you can recognize in the sky, Orion and Ursa Major are the two of this constellation that always consistently come up. And even if you look with your naked eye at Betelgeuse, you will realize that, at the constellation of Orion, you will realize that Betelgeuse is a very distinctly red star in the upper left arm of that constellation. Now, today we know that Betelgeuse is what we call a red supergiant star. It's quite evolved, and it's during its core hydrogen burning phase. Can be anywhere between 15 to 20 solar masses in mass, a few 100,000 solar luminosities, and a temperature of approximately 3,500 Kelvin degrees. But of course, the size, that's the name, red supergiant, indicates it has a sheer size of about 900 or so, maybe up to 1,000 times the radius of the sun. So it's a pretty big star. And the fact that it's relatively close, it's about a distance of about 200 parsecs away, but it's also a really big star. And those two facts together allow us to actually use interferometry to specially resolve the disk of another star, which is quite a rare and fascinating thing in astronomy. The only star we were able to resolve for many years is the sun. Most, as you know, the vast majority of stars it's like single points in the sky. So having the ability to completely image and resolve the surface of another star is quite fascinating. So Betelgeuse is in this, special group of small group of stars that we can spatially resolve. In the bottom, you can see a couple of pictures of Betelgeuse resolved by the very large telescope interferometry, as well as by recent data coming in from the ALMA array, as well as a picture from the Hubble Space Telescope that basically shows you that the environment around Betelgeuse is interesting as well. And as you can see, against the direction of motion, which is marked by this white arrow in this picture, there is a bow-shaped shock indicating that Betelgeuse is actually rushing through interstellar space, shocking environment around it. And as it turns out, recent measurements, including measurements that came in by observations that were taken as early as 3 years ago, indicate that Betelgeuse is speeding through space with a space velocity of approximately 30 kilometers per second. So it's quite fast. It almost makes it into the category of what we call runaway stars, stars that are speeding through the Milky Way galaxy with speeds higher than the average speeds of the stars in the field. So this is a fascinating star. Also, for yet another event, one other observable that I haven't mentioned yet, and that is when you look at a red supergiant highly evolved star, as I'll show you and I'll discuss more in detail later, you don't expect it to be rapidly rotating. Now, recent measurements of the surface rotational velocity of Betelgeuse indicated to be anywhere from 5 to 15 kilometers per second, which might not sound like a lot, but it's actually quite a lot for a star as big as Betelgeuse, as I will try to convince you later. So most giant and supergiant stars, the vast majority of them, neither are observed to have those kinds of rotational velocities. Also, they're not predicted by standard single star evolution to get to those rotational velocities. So there's two of those facts, the relatively rapid rotation of Betelgeuse coupled with its runaway nature are what I'm going to be trying to explain to you later with the model that I will be presenting. Now, if you were able to put Betelgeuse right in the heart of our solar system, right at the center in the sun, then it would overtake all of the inner planets of the solar system and all the way up to the orbit of Jupiter. It's quite a big star, again, as I mentioned earlier. But it's also quite a variable star. As a matter of fact, Betelgeuse is what we call a semi-regular variable star. And if you all remember, Betelgeuse made the news quite a lot about a year ago, December 2019, because it dimmed to unprecedented levels. Actually, you were able to go out at night with your naked eye and notice, without the help of any telescope, any instrument, any CCD, that Betelgeuse is noticeably dimmer. So here is a picture of Betelgeuse on the left from January 2019. And on the right, there is a Betelgeuse a picture of Betelgeuse at December of 2019. And as you can see, there is this big darkening going on in the bottom of the disk of Betelgeuse. Something is going on there that's causing 1 magnitude dimming of Betelgeuse. That you could actually, 1 magnitude is something that you can see with your naked eye, as I said earlier. So there's been a couple of ideas that have been suggested as to what is the nature of this dimming and what actually happened back in 2019. A lot of people, the news went a little wild, I would say, because a lot of people thought maybe that's an indication that Betelgeuse is going to blow up as a supernova explosion. As people working on supernova explosions, we love Betelgeuse partially because it's a really old geriatric star and will go supernova within the near future. And when we use the term near future in astronomy, of course, it could be hundreds of thousands of years instead of billions of years. And the idea is, okay, what actually happened when that great dimming occurred back a year ago? And two of the theories that were proposed was that perhaps there was a blob of plasma that was ejected in the south hemisphere of Betelgeuse almost towards the direction of the Earth, that then cooled down and formed dust. And this dust obscured part of Betelgeuse, causing it to dim. That's one of the ideas that were proposed out there. The other idea, it goes back to good old, star spots, and we know there's star spots. We study star spots in the context of our sun, but it turns out when you have a red supergiant, the combined magnetorotational effects can actually create even bigger sunspots, star spots. So one of the ideas was that perhaps you had the formation of a super spot, a big star spot on the surface of Betelgeuse that temporarily caused it to drop the apparent brightness. So we don't quite know which one of the two hypotheses is yet right. There's still a lot of vigorous debate in the community about that, which to me indicates that there is still a lot of interest in something that a lot of us astronomers are taking for granted because it's simply something we can just look out and see with our naked eyes, and that is the star Betelgeuse. Turns out to be way more fascinating than you would think. The other interesting observational fact about Betelgeuse, as I said earlier, is that it has a space velocity of about 30 kilometers per second, making it a runaway star, as indicated by observations that were taken over the last 3 years. Now, if you take the motion of Betelgeuse and extrapolate backwards, assuming a straight line, which of course is probably very wrong, but often that's what astronomers are doing in an effort to find what the birthplace of Betelgeuse is, then that comes close to the Orion OB1A star association. And sometimes it's very confusing to say that name because it reminds me of Obi-Wan Kenobi from Star Wars. So if I say that, it will be, a spelling error. So I apologize in advance. But if you trace the orbit and the motion of the space motion of Betelgeuse backwards, it seems to come close, but not quite at the Orion OB1A star association, which is the purported birthplace of Betelgeuse. Now, if you simply use that fact, how far away is Betelgeuse from Orion OB1A, how fast it's moving, and solve for time, right? The implied so-called kinematic age of Betelgeuse turns out to be about 1 million years, which means that potentially the star was ejected somehow from that birth cluster about 1 million years ago or so. But of course, as I said earlier, it's not quite, a straight line that you have to draw to come to the birthplace of Betelgeuse. That's not quite right. So there has been some work out there. Some authors have suggested that Betelgeuse has actually received 2 kicks. One dynamical ejection from its birth cluster early on, and later one by potentially a more massive companion that exploded as a supernova explosion. So, and again, the other observable that I want to describe and I want to explain with my model later on that I'm going to present to you, which was published earlier this year and presented to the American Astronomical Society meeting in Hawaii. The last in-person meeting that I was able to go to wasn't that bad. It was Hawaii. Is the fact that Betelgeuse is a rapid rotator. As a matter of fact, according to latest ALMA observations, it looks like it's rotating. And when I use the term rotating, I'm referring to V sin I because we don't quite know what the axis of rotation angle with respect to our viewing angle is of Betelgeuse. So, but the point is that the surface rotation of Betelgeuse ranges anywhere from 5 to 15 at the highest case, kilometers per second at the equator. And the error bar of that measurement, and that's very important, is only 0.25 kilometers per second. This is a very accurate measurement. And the fact that it's a very accurate measurement is very important because it allows us to rule out other things that may be happening, causing this rapid measurement of rotational velocity. And one of those things is large-scale convective motions. We know that red supergiants will have large-scale convective currents, and perhaps when you're actually measuring things, you're not quite measuring the rotation of the star, you're measuring those velocities due to those large-scale convective motions. Well, it turns out you can rule those out thanks to this really small error bar of this measurement. It has to be a true rotational velocity of the star. On top of that, there is some other interesting observable. Like if you take a spectrum of Betelgeuse and you measure the nitrogen to oxygen and the nitrogen to carbon abundance ratio, then you find those two ratios to be higher compared to standard solar values around the Milky Way galaxy, which means that there's some process in the star that led to the enhancement of what we call alpha elements like nitrogen in the surface of Betelgeuse. So the fact that you have this nitrogen enhancement in the surface of Betelgeuse could be related to enhanced mixing in Betelgeuse due to rotation, something that has been proposed and has been observed for other rapidly rotating stars that are not necessarily giants or supergiants. Also, there's been a lot of modeling that happened over the last few years in the community. There is a stellar evolution code that's very, very popular. A lot of people all over the world are using it, including myself, that indicate that if you were to start with a single rapidly rotating star at the 0 age sequence, even as rapid as close to breakup speed, then by the time it gets to the supergiant stage, due to angular momentum conservation and angular momentum losses due to wind mass losses, then it's really hard to produce a rapidly rotating supergiant, assuming single star evolution. So, all these facts together make Betelgeuse alone a very interesting star. It's a rapidly rotating runaway supergiant. So the question that were posed when we came across these observables is, how can you get that? How can you get a rapidly rotating runaway supergiant star like Betelgeuse? So as I mentioned earlier, there's been a lot of modeling of the evolution of rotating massive stars, anywhere from 12 to 60 solar masses. And some of the giants of the field have wrote, really extensive review papers like the one I'm showing here by Darren Maynette, that basically consistently always show that if you have a single massive star, no matter how fast it starts its life at the main sequence rotating, no matter how rapidly rotating it is at the 0 age main sequence, by the time you get to the supergiant stage, this surface equatorial rotational velocity will drop down to below 1 kilometer per second. That is consistently found across single star evolution models across the board so far. Indicating, due to the fact, of course, of angular momentum conservation and angular momentum losses that occur when stars are losing mass, it's nearly impossible to get a single rapidly rotating supergiant. There has to be some sort of interaction that led to the spin-up of a rapidly rotating supergiant star. So how can you get that? Well, there's three possible ways to do that. And one of those is the classic tidal synchronization effect in a closed binary star system. Well, in the case of Betelgeuse, this cannot work because it is unable to bring the stars any close to breakup rotation, and you would need to get there before the star expands to become a red supergiant to explain this, right before that happens, nevertheless, to explain the observed rotational velocity. The other alternative is that you could have mass accretion in a binary system from a more massive to a less massive star when the more massive star expands and fills its Roche lobe, the so-called Roche lobe overflow. And as you transfer mass to the smaller companion, you also transfer angular momentum via this accretion disk that's forming. And this can lead to potentially spinning up the envelope of the secondary, of the companion star. So then if you have that, and then the more massive star eventually, more massive stars live for less time. So if the more massive star explodes as a supernova explosion, perhaps, then that now rapidly rotating companion can escape the system with runaway-like space velocities. And the third possible case, and that's the case that we're making in this work, is that perhaps you actually had a binary, but you had a binary where Betelgeuse was the largest star with a lower mass companion. And as the largest star expanded to become a red supergiant, it engulfed this smaller, lower mass companion, then spun down its envelope, spinning it up. It's kind of like stirring coffee in a cup, right? That's the kind of mechanism, if you want to think about it in simple terms, that we think led to the spin up of Betelgeuse's envelope. And we're going to try to convince you by the end of this talk that this seems to be in agreement with those observations. So there was a recent result, looking at those three models, number one is already ruled out for the reasons that I described, marked with red text here. So it was really between 2 and 3, right? And there was a recent result, population synthesis modeling in Mesa, that was produced by a European group led by Matthew Renzo, that basically showed that supernova-induced ejection in a binary system is not quite an efficient mechanism in producing runaway stars. And I want to backtrack there for a second and introduce you to the couple of ways. I'm sure you've heard about them, but remind you the couple of ways that astronomers have proposed in order to produce runaway stars. And one of them is the supernova mechanism, the idea that you have two stars in a closed binary system, one of them explodes and the other one escapes with what its orbital speed used to be, which can be pretty high in some cases. The other scenario is that you have a young cluster of stars right after it was born, where it's more compact in the center. So there's a lot of gravitational interactions and flybys that occasionally eject one of those stars, a few of those stars away from the system. So those are the two ways you can get runaway stars. And it turns out, based on this recent result, that the supernova-induced ejection seems to be way more inefficient than it was previously thought in producing those runaway stars. So that's kind of like hitting number 2 a little bit, leaving us with more possibilities perhaps for number 3. So here's a few more reasons why accretion-induced spin-up is potentially hard to explain. And this is a figure from Selma de Mink, published in 2013, which shows you how the surface equatorial velocity of rotational velocity of two stars in a binary system evolves over time for different initial configurations. So for example, in the top left panel, you have a binary system with a 20 and a 15 solar mass star with an initial period of 25 days. And the dark blue line shows you how the rotational velocity of the smaller star, of the secondary, as we call it, will evolve. The lighter blue shows you how the rotational velocity of the primary will evolve. And in the 4 panels, you see different initial configurations and what happens for different things. And it turns out that if you're going to have accretion-induced spin-up, you will have to significantly fine-tune the initial binary parameters. And we know we in physics, we kind of like to steer away from fine-tuning. It seems to be more unlikely than it is, right? So this mechanism requires to spin the star up to near breakup velocities within a very short amount of time, right before the expansion of the star to become a supergiant, to explain the observed rotation of Betelgeuse at its current supergiant phase. So, but even after you have that, don't forget that Betelgeuse right now is a single star. So somehow you're gonna have to get rid of its companion, right? So if the progenitor of Betelgeuse was a binary system, something must have happened to that companion star. It either exploded as a supernova or it merged with Betelgeuse. So in this situation, in this scenario, the accretor would have to be exploded as a supernova. And again, as I said earlier, latest population synthesis modeling indicates that the majority of supernovae do not produce runaway stars. So there's a lot of fine tuning. There's a lot of things that you have to get just right and at the right timing for this model to work, making it kind of confined in the relative parameter space. Now, the model that I will present to you is kind of like a 2-step model. Remember, we have to explain the runaway nature of Betelgeuse and also simultaneously its rapid rotational equatorial velocity. It's rapid rotation as a supergiant. So we're going back to the alternative when it comes to how do you produce a runaway star. We go back to the classic ejection scenario, dynamical ejection scenario in young cluster. So assuming that Betelgeuse was born in what is now the Orion OB1A star association, a few million years ago, that was a much more compact cluster of young massive stars, potentially up to 10,000 solar masses in total. And the idea that we had in collaboration with my collaborator here, Alexei Bobrik from Lund University, was to use an n-body gravitational interactions code to simulate the interactions between young massive stars in such a cluster. So we used the few body, which is such a code, to model those n-body interactions and then predict how many binaries, intact binaries, will escape the system. So the fraction of binaries to escape the system, but also in the desired mass ratio and separation, binary separation, that will allow us later, if we had a merger after the ejection, to provide the star with the rapid rotational velocity. So By far, the most efficient way to eject stars in a young cluster is binary flybys in this case, where you start off with a cluster, 50% of your stars are single, 50% of your stars are in binary stars, and massive binary flybys is found to be the most efficient way to produce runaway binary systems. So, and it turns out that you need high mass impactor binaries to make that happen. So what am I showing you here in this quite rather complicated figure? Well, what I'm showing you is the parameters of ejected binaries that we find for different cases from this n-body simulation. So there's 3 different cases here. In one case, we're looking at binaries ejected where the one star had 17 solar masses and the secondary had 3 solar masses. That's in the bottom left. In another case, we're looking at a 15 and a 1 solar mass binary. And in the other case, we're looking at a 16 and a 4 solar mass binary. And remember, the key here is that you got to eject those binaries while they're still gravitationally intact. You don't want to disrupt those boundaries during those interactions. Otherwise, you're not going to get an ejected binary from the system in runaway speeds. So what I'm showing you here in those plots on the y-axis is the binary separation of the ejected system. On the x-axis is the space velocity of the ejected binary measured in kilometers per second. So as you can see now in those lines, the vertical red line indicates which binaries are runaway. Anything right from the vertical red line is a runaway binary, and the horizontal red line indicates which binaries were ejected with an initial separation larger than 200 times the radius of the sun, 200 solar radii. And you need those kind of initial separations, as you will see later, to explain, to get to this spin up in the envelope once the merger occurs. So we really want systems that are ejected in the upper right part of this diagram. And now if you focus in the upper right parts of those diagrams, you will see that there's obviously a few systems only that fulfill this criteria, right? But they're also colored, and those colors mean something. The color of its dot represents the mass of the impactor, the star that caused the ejection via this dynamical interaction. And usually it's not just a star, it's another massive binary. And as you can see, as I said earlier, you need pretty massive impactors, more than typically 30 to 40 solar masses to eject those kind of systems intact. So again, the reason I'm showing you this is, okay, first we had to ask the question, how do we get intact binaries that are ejected from birth clusters with runaway speeds at the right initial separation? And then once we have those initial models, then we were able to go to step 2, which was, okay, now you have this runaway binary between, say, a 17 solar mass and a 3 solar mass star. What happens when there is a merger between the two? Will that lead to a spin up of the envelope? And that's the second part. So to simulate this merger, we had in our first order of business was to do this as simply as possible by using good old analytical formulas, right? And to do this, of course, the handicap there is that you're gonna have to adapt some assumptions. So the assumptions that we had to work with in this particular model is that we had to assume an initially low mass ratio binary, meaning that the difference, the ratio between the mass and the primary and the secondary is very low. And as you can see from the models that I discussed earlier, I'm looking at 17 plus 3, 16 plus 4, or 15 plus 1. So those are fulfilling this kind of criteria. The second assumption is that the merger is triggered due to the contact that happens once the massive star expands, or it goes through the so-called Hertzsprung gap crossing phase, post the main sequence. Once the star runs out of hydrogen in the core and expands to become a red supergiant within a thermal timescale, it moves in the HR diagram through this Hertzsprung gap phase. And this is when it expands. This is when its radius becomes larger and larger. So we say that the merger is triggered because of that event, because of the fact that the primary expands, thereby engulfing the much smaller secondary, which is still in the main sequence. And then this engulfment leads to a spiral in of the secondary within the envelope of the primary. And the reason for that happening is because now the secondary, the ambient environment of the secondary has higher density. So it experiences a drag force, the form of which I'm showing you here in the bottom, which causes its orbit to slowly decay. And there's some other assumptions we have to maintain to have a closed system of equations, that the secondary maintains near Keplerian speed during its spiraling in, that we ignore changes in the secondary structure and any nucleosynthesis as well. And it turns out number 7 as well, which is the entropy of the primary envelope remains unaffected, is something we can show quantitatively that that's the case largely. So if you take this form of drag force and use the good old, Newton equation of motion with this force, then you can also calculate what is the angular momentum deposition that occurs as the secondary is spiraling in the envelope of the primary. So you can essentially find how much you are perturbing the original angular momentum of the primary before the merger. So the primary before the merger already had some spin, it already had some angular momentum, but as the secondary now is spiraling in, kind of like stirring the coffee inside a coffee mug, it's depositing angular momentum and it's spinning up the envelope of the secondary. And you can calculate with this analytical formula under this assumption what that perturbation is. And that perturbation comes out to be that equation in the bottom that I'm showing you. Now, if you take that equation and you initialize it in a stellar evolution code and see what happens when the star evolves in the red supergiant stage, in the current stage of Betelgeuse, you can see whether you get the correct surface equatorial velocity or not. And that's what we're going to show you later. But before we get there, it's always good to talk in terms of equations, but sometimes it's better to talk in terms of pictures. So let me see if I can show you a picture here of what that model looks like. So now remember, you have ejected a high mass ratio binary with runaway-like speeds, 30 kilometers per second or more, from a birth cluster. So that binary is moving through free space. And in that binary, let's just say that the primary is anywhere from 15 to 20 solar masses, close to the current mass of Betelgeuse. And the secondary is like the sun, it's 1 solar mass, much smaller. And in this particular example, the initial separation between the stars is anywhere from 200 to 300 solar radii. So then the primary obviously evolves faster, runs out of hydrogen in the core, and enters the Hertzsprung gap crossing phase. The envelope is expanding. And as the envelope is expanding, of course, it engulfs that secondary. Then because of this engulfment, the secondary is experiencing a drag force that leads its orbit to decay. And as its orbit decays within the envelope of the primary, it gets closer and closer to the core, which is now, of course, a helium core, indicated here with the green color, the core of the secondary, which eventually, when it crosses the so-called tidal radius, gets completely tidally disrupted and merges with the core of that primary. So at this point, a lot of interesting dynamical physics is taking place, and you really need a multidimensional hydrodynamic simulation to capture this or accurately. But simply put, the secondary merges with the core of the primary. There's some extra fresh material from the secondary that you're feeding the core right now. You're kind of rejuvenating the core of the primary with extra hydrogen. At the same time, you may have a pulse, you may have an outwards kind of momentum that can cause, in some cases, mass loss. So that happens in number 4. So this is kind of like the model that I'm showing you here. This is what we think is causing the spin up of Betelgeuse. So how do we quantitatively support this model, and how do we compare this against the observations of Betelgeuse? As I said earlier, we're using the one of the most popular and most widely spread open source codes to model the evolutions of stars with many different features. I highly recommend it for students that want to get into stellar astrophysics. Mesa is an incredible tool written by very talented people. So Mesa stands for the Modules for Experiments in Stellar Astrophysics. So what we do is we take this originally perturbed angular momentum profile. And then we import it, we initialize the secondary after the merger with this perturbed profile. And then Mesa is solving all the equations of angular momentum transport, which, when you have a rotating star, you basically have two effects. You have the diffusion of angular momentum between the envelope and the core, but you also have mixing. You can induce mixing due to rotation. And so Mesa can calculate all these effects and make predictions about what's going to happen to the star. It can make predictions about what the luminosity and the effective temperature of the star will be at a certain time later on. In other words, the Hertzsprung-Russell diagram track. It can predict what the surface rotation will be like. It can predict what the surface abundances will look like. So by initializing our perturbed primary with this equation, we can make those predictions. See if we get anywhere close to what Betelgeuse looks like. So first, we wanted to just go back to what people have already done, just to prove to ourselves that yes, there's no way, independently prove to ourselves that there's no way you can get a rapidly rotating supergiant star if you just had single book, textbook standard star evolution. So in this case, we looked at a 15 solar mass star and a 20 solar mass star, and we calculated the evolution with Mesa. And what I'm showing you here is the Hertzsprung-Russell diagram. This cross on the right is basically the 2 sigma observations of Betelgeuse. So this is where Betelgeuse is in the HR diagram. So as you can see, those are the 2 sigma error bars from the latest observations. So while you can get, within 2 sigma of during the red supergiant stage of Betelgeuse, and that's good, you can get a red supergiant. The problem is that if you just have single star evolution, you never get rapid enough rotation to explain the observed 5 to 15 kilometers per second rotation of Betelgeuse. So the next step for us would be, of course, to actually look at the merger scenario. And for this, we've looked at primary stars between the mass ranges of 15 to 17 and secondaries in the mass range between 1 and 4 solar masses. And I'm not going to go through this table. I don't want to confuse everybody, but I'm showing you this here. You can find more details in our paper, but I'm showing you this here to show you kind of like the parameter space that we've looked at when we did this calculation. And I will pay more focus in this for this particular presentation in the last model in the bottom, which shows the binary merger between a 16 solar mass star and a 4 solar mass secondary. So when we did that with Mesa, we can again, of course, produce the HR diagram under the assumption of initial conditions. And the initial conditions we looked at was the initial, remember, separation of the binary. So when the binary is expelled from its birth cluster, what is this initial separation? Is it 200, 250, or 300 solar radii? So we looked in those different values to just play around with the parameter space and see how consistent we are and how degenerate the parameter space is. And if you do that and everything passed, there's a little gap in all those HR diagrams, this is where the adjustment happened. This is where we took the perturbed profile following the merger and mapped it back to the original profile of the primary. And then everything with the colored dots is what happens to the primary after the merger. So it's the post-merger phase, in other words. And again, you can see the location of Betelgeuse in the HR diagram. And the colors in this case indicate surface equatorial rotational velocity. So the bluer it is, the lower the velocity, the redder it is, the faster the spin of the star. And as you can see, for all those cases, for this particular model, we're getting quite close to the observed location of Betelgeuse in the HR diagram. And although it might not be initially obvious that the surface equatorial velocity is actually high, because we're talking, we want to get to 5 to 15 kilometers per second, it turns out for that to be the case as well, as I'll show you in a second. So here is the evolution of the surface rotational velocity of the post-merger star as a function of time. So in the top left plot, what you see is plain old single star evolution. And again, as you see, it immediately, when the star becomes a red supergiant, immediately gets to the really, really slow rotation levels. And I do want to point out that those horizontal dotted lines basically indicate the observed rotation of Betelgeuse from 5 to 15 kilometers per second. And then on the other panels, you see the three different binary models and post-merger models that we looked at. And as you can see, for all of them, you can maintain a rapid rotation in the surface for a few hundred thousands of years. And in particular, we're looking at the 16 plus 4 case, which is the bottom right plot, where you can clearly see that following the merger, the primary envelope, the surface of the primary is indeed rotating with this really rapid speeds for a red supergiant. On top of that, we didn't stop there because, as I said earlier, Mesa can also predict, following angular momentum diffusion and mixing, it can predict what the surface abundances of Betelgeuse will be at that phase. So we calculated what the model told us, that the nitrogen to carbon and the nitrogen to oxygen ratios at the surface will be. And we found them to be very consistent, really close to the values that have been measured for Betelgeuse, 2.9 and 0.6 respectively. So now we had 3 pieces of evidence that made us hopeful that perhaps our model is really something that is of value when it comes to explaining this bizarre nature of Betelgeuse, at least its rapid equatorial rotational velocity and its runaway nature. And both the HR evolution in the HR diagram, the observed surface abundances, as well as the observed rotation were found to be consistent with the observation. So of course, we don't want to stop there. Remember, that was a model that we devised based on analytical estimations. Now what we're working on, we're taking the next step. And the next step is to do the problem more accurately by actually modeling the merger of the 2 stars using an adaptive mesh refinement 3D hydrodynamics code. And we have one of those tools here at LSU developed in-house. It's called OctoTiger. For those that don't know, the tiger is the mascot of Louisiana State University, and we tend to name everything after our mascot here at LSU because football is religion here. So American football, that is. So on the left, what I'm showing you is one of the early calculations that we've run, which shows the merger between a 16 solar mass primary and a 1 solar mass secondary. So the green that you see is actually the envelope of the primary, and the red, the two red dots. In one case, you have the core, the helium core of the primary. On the other case, you have the incoming 1 solar mass secondary. So as you can see, it's pretty much the picture that I showed you in a kind of like a cartoon version earlier on. As the secondary is approaching the core of the primary, eventually gets this nice teardrop shape, indicating that it's merger and its tidal disruption from the core of the primary star. And on top of that, you can see other interesting features here. You can see this spiraling outflow of material, which goes back to the fact that when you have a merger between 2 stars, it's quite likely you will have the ejection of some material. You might have some post-merger mass loss, and that's another thing that we want to look at down the road. But if you take now this 3-dimensional simulation of a merger after the merger has occurred and calculate the angle, because remember, this is a 3-dimensional data structure here. So if you were to have any hope of mapping that into a stellar evolution code, we can't yet do stellar evolution in 3D. You will have to somehow turn this 3D data set into a spherically symmetric 1-dimensional data set that you can map into Mesa and see what happens in the future. So if you were to take an angle average, angular momentum profile of the post-merger object, and that's what the rotational velocity as a function of radius would look like. That's the plot on the right. That's what we want to map into Mesa to see what happens in the future. Of course, in this simulation, we had a problem. And that problem was the fact that we were confined by computing time and resolution. This is why in this particular simulation, the initial contact radius, the initial separation of the binary is only 12 solar radii. But if you start the merger at 12 solar radii, you will not really get as high of a spin up as you would, obviously, if you start the merger when the primary is at a larger radius. But if you try to simulate that in 3D, that's quite challenging because you need a bigger simulation box and you need to resolve the structure of a tiny 1 solar mass stellar star inside the low density large envelope of a 16 solar mass star. So there's a lot of numerical issues there that we're working on to make those kind of larger scale, larger radii mergers happen in our supercomputers. But once we get to that point, we'll have a more realistic initial condition to put into Mesa to see what happens when the star evolves to the final red supergiant state. So that's the next step that we want to take with this work. And to summarize everything, Betelgeuse is a very, very special star in the night sky. We cannot take it for granted. It proved to us how special it is last year with its incredible dimming event. For me, it's special because it's one of those rare situations when you have a rapidly rotating runaway supergiant star. And we are proposing here that you can explain this nature of Betelgeuse by invoking a dynamical ejection of a high mass ratio binary in a young cluster, Orion 1B, OB1A, followed by an early, what we call early case B merger, meaning right after the main sequence. That's when you have the merger. And the merger is triggered because of the expansion of the primary, which engulfs the secondary, which then spins down, which spirals in and spins up the envelope of the primary. So the angular momentum deposition that occurs during that merger can indeed, according to this models, lead to significant spin up of the primary envelope that can last for a few 100,000 years, explaining what you see with Betelgeuse. And we get agreement in terms of the way that our models evolve in the HR diagram. They end up at the right place within the observations, within the 2 sigma error bars of Betelgeuse. The predicted surface abundances are in agreement with the observed ones. And out of all the models we run, we found the 16 plus 4 solar mass merger to be the closest one to the observation. So that's the one that I've decided to show you here in this presentation. So in the future, again, we plan to use more realistic 3-dimensional merger hydrodynamic simulations to explore these effects. And there's a lot of challenges, as I mentioned, going into that. Resolution challenges. You have this really high density contrast between the secondary and the ambient envelope material of the primary, which is really hard to resolve properly. It takes a lot of resolution and a lot of computing time. So we're trying to work those problems out to get to that next phase. And there's, of course, way more things you can look at, because it turns out that, as you know, more than 50% of stars in the Milky Way galaxies are thought to be in binary systems. Now, 1/3 of them are thought to be experiencing a merger at some point in their lives. So mergers are quite an important and overlooked aspect of stellar evolution that traditional stellar evolution hasn't really addressed. So part of the big effort that we're going to put forth here at Louisiana State University is to look more closely at, with more physics and more accurate prescriptions of what happens when 2 stars merge, in all kinds of observables associated with those mergers. I do want to note that sometimes those mergers are called merge bursts because they lead to a transient event. And I know we have some people here like George who likes transient astrophysics as much as I do. With the upcoming era of the Large Synoptic Survey Telescope here in the United States, the LSST, we're going to be finding millions of transients every night. And perhaps some of them will be associated with the merger of 2 stars, producing a flash. So part of the work we want to do is to simulate those flashes, to do the radiation transport and the radiation hydrodynamics associated with this kind of mergers in order to make predictions, to predict light curves and spectra that can drive the future observations. So hang on, it's going to be a really exciting time for transient astrophysics, and mergers like the one I was discussing today may have a lot of role to play there. So I do want to thank everyone for your attention and the honor to allow me to speak and open it up for questions. So I'm going to leave you with a real picture of dimmed up Betelgeuse from 1 year ago. Is it the result of a merger? And what we find is that evidence points to the fact that it probably is. The possibility cannot be ruled out. The alternative scenario, it's much less likely, that of the accretion-induced spin-up. And also, again, as I said earlier, remember that most massive stars are in binaries, and a significant fraction of binaries merge, and we still are early on in our understanding of how that affects stellar evolution and the endpoints of massive stars. So that, I want to thank everyone.
Thank you very much, Mano, for a very interesting talk. Questions? People may raise their hands or just take the floor since.
Can I ask a question, Vasily? Nikos. Mano, impressive results. Congratulations. I am impressed with what you said, among other things, with what you said about the abundances, and that you fit the abundances. And my question is, do we know the interior of such stars so well as to be sure that perturbation of that interior is believable?
That's a very good question. Thank you very much, Nick. So obviously there is a large uncertainty in terms of figuring out the exact interior abundances of those massive stars. So the best you can do when you do this kind of modeling is start off your calculation by assuming a certain metallicity, which is taken to be the observed metallicity in the neighborhood of where Betelgeuse is located, so close to solar. And based on that initial metallicity at the zero-edge main sequence, then you let nuclear burning and mixing essentially do the job. So you have several mixing mechanisms that are included in Mesa. You have the good old classic convective mixing, but you also, of course, have rotationally induced mixing, magnetic mixing, and all those mixing prescriptions are parameterized, and they make, based on this initial abundance profile that you start off at the zero-edge main sequence, can make a prediction about how much of this material that you make in the core is transported effectively or efficiently into the surface. So that's as much as you can do with what you have. But in terms of observations, you're right. You know, it's still quite hard, even with making use of some asteroseismological observations. We've made some leeway, but it's still hard to predict 100% accuracy what the initial interior abundances will be. Or the best you can do is to start with those assumptions. I hope that answers your question.
Okay, thank you. Yes.
Okay, someone else? Since no one is taking the floor, I would like to ask something. Mano, when the secondary star is being accreted, right? Is it completely destroyed through tidal forces? And because I was wondering, for example, what happens to the core of the supergiant, right? Is this core, in a sense, how is it supported? Is it inert, the core, so it's electron pressure? And how?
By angular momentum barrier, because it's rotating, but it is inert indeed. But the idea there is that, you know, the secondary star will not be disrupted unless it crosses the tidal radius. And it turns out that this tidal radius for this particular system is right outside, maybe 2 times the radius of the helium core, what you see here with the red color. And when that crossing happens is when you actually disrupt the secondary. Now, when the secondary is disrupted, is accreted, as you mentioned, on top of the helium core now of the primary, which means there is another effect which we are discussing in the paper, which I didn't have time to go into here, which is called rejuvenation, because suddenly you're adding fresh fuel from the secondary. You know, you have a, say, 70% hydrogen, 28% helium star, and you dump it into the core of the primary. So right now you got fresh fuel that initially had been mostly depleted throughout the main sequence to provide the core with more burning. So that extra fuel actually has a small, depending on what the initial mass ratio is, and that effect, of course, is all over the map for different initial conditions, you could have a case where an initially red supergiant star, and that to me is fascinating, instead of becoming a red supergiant, will change course and become a blue supergiant because of this included luminosity that you're going to be producing from the core. That's going to lead to increased mass loss, for example, driving the evolution towards the blue. So as a matter of fact, there was a paper 3 or 4 years ago by Manon, where they looked at the progenitor of supernova 9087A. As you know, we have pictures, we have observations of archival observations of that progenitor before the supernova took place. And what they were able to deduce was that it had to be the result of a merger that was rejuvenated. And they had a lot of modeling and consistent with the evidence to support that. So now we think, the vast majority of the community thinks that the progenitor of 9087A was a blue supergiant that was a result of a merger that happened in the past, based on those observations. So what you have here, yes, it's what we're trying to do with those hydrodynamic simulations. Another step that I forgot to mention is actually add nuclear synthesis. So we will add some nuclear burning and a nuclear reaction network into those octotiger simulations to accurately estimate the magnitude of the nuclear energy that's generated when the secondary burns up in the core, which can have implications for what happens to the primary as well. So in this particular example, in those mass ratios that we investigated, all of those primaries end up becoming red supergiants. But if you had slightly lower mass ratio, if you had a bigger secondary, then you could get, which is the case for the progenitor of 9087A, you could get a blue supergiant. So this is what goes back to what I said earlier, that we always think we have stellar evolution right until you add the binary evolution into the mix, and then you add merger into the mix, and then it becomes way more complicated for a lot of these massive stars. So.
Okay, thank you very much. Then we have some raised hands. Ming, maybe you can start, and then Adonis, and then Kostas.
Hi, this is Ming Yang from National Observatory of Athens. Very nice talk. And my question actually is that, did you imply any variability in your model? For example, because I know that Mesa can implement some radio pulsation model that you can produce the light curve. And also, is that possible? The merger could trigger supernova explosion instead of just become a stable star. Yeah.
Those are both very, very interesting and timely questions. So coming to your first question, we did not look at variability specifically. We just wanted to focus on the three main observables, but that's part 2 of the work we're doing right now. As you mentioned, Mesa can make asteroseismologic prediction, which essentially would provide you with a prediction of the variability of Betelgeuse. We're not yet aiming to work on describing the dimming when it comes to the great dimming of 2019. When it comes to variability, there's a lot of other great groups that are working hard on that. We're rather focusing on those long-term evolution picture. And coming to your second question about whether a merger can lead to a supernovae, the answer is quite possibly yes. You could have, there's a model, there's a paper that came out last year that basically said that, you could have a merger right before the end of the life of, let's say a 4, 5, 6 solar intermediate mass star, which would drive the young white dwarf that has been formed in its core towards the end of its life past the Chandrasekhar limit. So you could have a merger like that within the envelope, within the common envelope, to use a more appropriate term, of this kind of situation. You could have a type 1a supernova exploding within a common envelope. So there's 2 kind of ways to look at it. Yes, you could have a type 1a event happening in the envelope involving the explosion of a white dwarf, or in some cases, you could drive the core of an even more massive star faster towards collapse and kind of like trigger supernova. So those things have not quite been looked at yet with great details. So we know those things are possible, but there's still a lot of work and a lot of simulations that need to be done to verify those kinds of ideas. I will say that some of the more massive stars in the Milky Way galaxy, and when I say massive, I'm referring to 150 to 200 solar mass stars. The most massive star we found in the Milky Way is close to 300 solar mass stars, as a matter of fact. Those stars die via a completely different explosion called peristability supernovae. I'm not going to get into the specifics, but they incur an instability in their carbon cores if their carbon cores is larger than 60 solar masses. So in those cases, if you dump more mass into that massive star because of a merger, then it's going to go peristability supernova. And something like that was actually also recently proposed by a group out of Santa Cruz. So both of your questions are definitely merit more work, but people are working on this direction.
Caristo, thank you.
Thank you.
Okay, thank you. Adoni?
Hello, thank you, Manos, for very nice talk. I have one rather naive question and a second one, which is a bit more technical. My rather naive question is that I never thought of Betelgeuse as a massive star, to be honest. And to be honest, I don't remember the spectral type, but I always had it that it is very close to the spectral type of Sun, or even later.
K23.
K23, which is maybe adding a bit of implication with its mass, right?
Well, it's its mass and the fact that it's a supergiant, right? It's a very large, red, cool envelope star. So
yeah, but at the zero age, what would be the mass of the star? If the spectral type, it's not an early type star, right?
Oh, you mean at the zero age? That would probably be a very blue star. It would be an OB type star. If it was
the zero age was an OB.
Yes.
Mm-hmm. Okay, this makes sense.
Yeah.
So one question was about this because I had a feeling that it is quite late and the mass is confusing. The second question, I guess it's more technical because you showed somewhere your parameter space. I guess this is from Mesa simulation and not hydro simulations, right?
Those parameters?
These are for Mesa, not for your hydro code.
Correct. The hydro code, this is what I showed you here, is just the first step of the next part of the work we want to do. We haven't published that yet. So we're now working on those simulations. This data here is from the paper that we published. That is from the Mesa one. So yeah.
Yeah, and the last part is how much is the characteristic time scale of your merger if you have this information from your code?
Yeah, we definitely do. The merger takes place within a few days.
Mm-hmm. So it is consistent with the variability that you see on Betelgeuse.
The time scale of the merger is faster than the thermal expansion time scale of the primary star to become a red supergiant. Remember, the merger happens earlier. It happens at the end of the main sequence. It doesn't happen now when the Betelgeuse is now where we observe the ability now. So.
Okay, nice.
Sure.
Thank you very much.
Thank you. Good to hear you.
Yeah.
And Kostas Gourgouliatos. Costa?
Yes, hello. Thank you very much for the great talk. I enjoyed it very much. I have a question that is related to Mesa. Being a one-dimensional code, is it going to, would the use of Mesa be able to answer questions that are related to, let's say, dimming of Betelgeuse or these sort of effects? And judging, for instance, from the image that you showed, some things seem to be intrinsically three-dimensional. So what do you believe that we will be able to resolve, and what are the things that we will need a more sophisticated calculation to understand?
Thank you, Kostas. That's another great question. I keep getting really great questions from you guys in this talk, so I appreciate it. So when it comes to Mesa 1D stellar evolution, of course, that comes with certain kind of approximations. But again, I do want to say that's kind of like the state of the art in the sense that computationally you cannot do 3D stellar evolution. So what Mesa can do in terms of the variability and the dimming of Betelgeuse, at the best case scenarios, can give you some modes and some that could translate to a certain luminosity variation that you could correlate with the observations. But it will have to be an averaged out kind of situation, right? So you have to think of what Mesa is predicting as as an averaged out situation of what really happens in a three-dimensional star. Now, there are efforts by groups to simulate the great dimming, or at least the early stages of the great dimming under those two different scenarios that I'm showing you here, using three-dimensional magnetohydrodynamics codes. Because, for example, if you were to look at the giant star spot explanation, then all of us know that the reason star spots exist is because you are inhibiting convection due to the magnetic field energy density. The magnetic field energy density inhibits convective motion, so that area of the star appears less bright than the rest. So people, to do this simulation accurately, you got to use magnetohydrodynamics, as you mentioned, in 3D. There's people working on those kinds of stuff in a very, very complicated, very expensive, some of the most expensive computer simulations you can run. As a matter of fact, the latest one that came out, I think it was approximately 20 million CPU hours or something like that. It's very expensive and challenging. So yes, you can tackle this problem both ways, but of course, when you do it with Mesa, all you can do is a general prediction of the variability based on those modes. With 3D codes, you can't do it for a long time scale, but you can at least understand the early stages of what leads to something like a giant star spot to explain this kind of phenomenon. So yes, 3D is the future. As a matter of fact, later this week, I'm going to be part of a virtual conference where we're going to be discussing what we need to do in the next 10 years in terms of exascale computer simulations, which are coming. They're down the road. There's already the Aurora exascale machine that's being administered in order to address better those kinds of problems. So just hang on. Computers are getting older with us and getting better than us too. So.
Okay, thank you very much. I don't see any other hands being raised. So
can I ask something
yes.
else? Okay. Yeah. This resembles a lot of the case, I don't know if you know it, 1309 Scorpio, merger of a contact binary.
Oh yeah, the 1309 Scorpio. Yeah,
yes.
Have worked on that system for a long time. Yes.
Yes. So maybe this indicates that binaries indeed pass through this contact phase, and this is not very rare. But because this contact phase, in their case, is relatively short and quickly leads to a merger.
Right, correct. You could have a contact phase that actually gets reversed in some cases, leads to a separation, but in many cases it leads to a merger. That's right.
Okay, what is the critical parameter in your simulation to develop instability during the merging period? Is it the mass ratio?
It is indeed the mass ratio. It's the most important.
It's the same with contact. This is why I'm asking you. Yeah.
Correct. The mass ratio is, and that's why we were limited towards higher mass ratios, because for larger mass ratios, you wouldn't get the same kind of effect. Never mind the rotation. The secondary parameter for our model, of course, is the initial separation, because you need that to spin the envelope high enough. But the mass ratio indeed is really the controlling parameter here.
Okay, and the second question has to do with the current situation of Betelgeuse. I mean, you are talking about the falling, the fainting episode. What about its current situation?
Right, yeah, we haven't, obviously it's back up, although I think there was another smaller dimming that happened a few months ago, but we haven't addressed that, and we haven't even attempted to work on that kind of aspect, because our models that we're running, they're not looking at those three-dimensional effects that the other person earlier indicated. We're not looking at large-scale star spot effects or the episodic ejections. So there's still things you can do with pulsation modes, as mentioned earlier, but we haven't yet gotten to focus on that. We initially just wanted to focus on those three main observables: the abundances, the rotational velocity, and the observed luminosity and temperature of Beetle Juice.
Okay, thanks.
Thank you.
So if there are no more questions, we would like to thank Manos once more for an excellent talk.
Thank
And
you all.
we'll see you all in a month with our next Hel.A.S monthly colloquium speaker. Have a good day, and to you, Manos, and good evening to all of us here in Greece.
Take care of yourself. Thank you. Good to see you. Bye-bye.